Alright, in this video we're going to be talking on tests for carbonyl groups. Now, we know there are two different types of carbonyl groups. That's the aldehyde and the ketone. And the major difference is just the presence of a hydrogen in the aldehyde group. This is aldehyde, and that of the ketone group is the presence of no hydrogen and two different carbon chains attached to it. That's the major difference between the aldehyde and ketone group. But now in this video, we're actually going to be talking about a general test, not a test to differentiate between these two groups. Certainly there are tests, but this one is a general test for carbonyl groups. So that's what we're actually going to be talking on. So let's go on. A carbonyl group could either be an aldehyde or a ketone, like I said earlier. An aldehyde group has one alpha carbon attached to the carbon bearing the functional group, while a ketone group has two alpha carbon attached to the carbon carrying the functional group. Now, we can see from this, we can actually call these the alpha carbons because they are directly attached to the carbon carrying the functional groups. And if there are other chain carbons, we can start naming them beta and so on. But these ones, they are actually called the alpha carbon. Now, the aldehyde, one hydrogen, the ketone, no hydrogen, but two alpha carbons. Now, this affects the reactivity of the carbonyl groups. Now, due to the presence of these carbon chains actually affect the reactivity of carbonyl groups, and at the end of the day, we end up finding out that the aldehyde group is more reactive than the ketone group. Why? The effect is what I illustrate as our next point. That is steric hindrance or steric effect. I don't know, I made a video on steric effect earlier. You can go and watch it out, but let me just give you a list of what I'm talking about now. Now for the ketone group, let's say we have something like this, and this is the carbon bearing the functional group, and these are other carbons. Let's say we have something like this. These carbons, they bear their own groups. They bear their own groups like this. They bear their own groups. Now all this carbon, imagine an attacking nucleophile and attacking electrophile is trying to bond with this. Before it could end up attacking this carbonyl group, maybe it's trying to displace this O, or it's trying to attach to it and maybe form a carboxylic acid. Before it could actually displace this group or actually bond with it, it's going to be hard because it's actually going to bump with this carbon, bump with this carbon, bump with this carbon, bump with this carbon, and it's not going to be easy for it to actually bump with this final carbon, and that's actually going to affect its reactivity. But for the aldehyde group, we see there's a hydrogen here. That's actually going to influence its reactivity. I'm just actually giving you a summary on all this steric hindrance and effect. You can check a previous video which I gave on this, and you can actually understand steric effect and steric hindrance. Just know that it affects the reactivity of aldehyde and ketone groups. The aldehyde compounds tend to be more reactive than the ketone group due to the fact that they possess one alpha carbon, while the ketone group has two, and due to the higher percentage of unreactive groups, what should I call them now, the methyl group, or let me just say carbon group, that are unreactive, they tend to reduce the reactivity of the ketone group. That's just what the point is talking about. Now, there are certain tests used to test for the carbonyl group in general, but there are also tests used to differentiate between the aldehyde group and the ketone group. But in this video now, like I told you earlier, we're actually going to be focusing on the tests. We're actually going to focus on the tests to actually test for the carbonyl group, not to differentiate between the carbonyl group and the ketone group. Now, there are two tests actually we're actually going to be talking about in this video. That's the test with BRADY'S reagent and test with Iodoform. Now, let's start with the first one. Test with BRADY'S reagent. Now, BRADY'S reagent, also known as, this is a K. BRADY'S reagent, also known as 2,4-dinitrophenylhydrazine, is a common reagent used in the testing for the presence of carbonyl groups. It is mainly a condensation reaction. That is the loss of water. That is, in this reaction, what actually happens is water is lost, and then the product actually combines to lead to the formation of another organic compound, and the organic compound is actually called hydrazone. I didn't include it here, hydrazone. That was actually going to be formed, and that hydrazone is a yellow crystal and that's what's actually going to be formed. On hitting after the reaction, on hitting it to actually activate the reaction or make it happen faster, the hydrazone will actually be formed, and the hydrazone is a yellow crystal, and once that yellow crystal is formed, you can actually detect if that compound is a carbonyl compound or any other compound, and if it's a carbonyl compound, you can actually then focus on our test to differentiate if it's an aldehyde or a ketone. But for now, we are only testing for carbonyl compounds. Now I want to give you the mechanism of the reaction. Now I said 2,4-dinitrophenylhydrazine, that's this, NH, double bond, and this is, no, a single bond, sorry, a single bond, N, H2, is a benzene ring, 2,4-NO2, 4 position NO2. This is 2,4-dinitrophenylhydrazine. Sorry, let me just make this. This is NO2. This is the 2,4-dinitrophenylhydrazine. And like I said earlier, this 2,4-dinitrophenylhydrazine will react to the carbonyl group. Or let me just give you, this is the carbonyl group as we all know it. I'm not going to be putting it in position so we can actually see it at ease, and it will be easy for us to differentiate. Now, like I said earlier, what's actually going to happen is a condensation reaction. That's the loss of water. And we can see that this H2 present here will end up taking this oxygen from the carbonyl group. And when it takes the oxygen, what's actually going to be formed is water. And that's just like the simple mechanism of the reaction. There are actually steps which you follow to take for this reaction to occur, but I don't want to bore you up with the steps, so let me just give you this. This is like the simple test that we're actually going to observe. Like, water is actually going to be formed. The water is actually going to be taken from 2 hydrogen from the amide group and 1 oxygen from the carbonyl group, and that will lead to the formation of water, and therefore this bond will actually come here and bond with this nitrogen, and that will lead to the formation of our hydrazone. Now our hydrazone can be represented by this. This is our hydrazone. This is a single bond N. Now this double bond will end up coming here to combine with this, and we can actually include our benzene ring. Now this is our benzene ring. And at the end of the day, with our nitro group, NO2 and NO2 plus H2O. And that's actually what just happens in this reaction. Now these are 2,4-dinitrophenylhydrazine, and these are hydrazone. That's just everything that happens in this reaction. This is a yellow crystal, and once this yellow crystal is observed on heating or leaving to stand for a while, we find out that hydrazone is formed. We don't need any further tests. This will just tell us that we are dealing with a carbonyl group. So in our inference, we can actually just write carbonyl compound present. Now that's just all. Now, BRADY'S reagent, that's the 2,4-dinitrophenylhydrazine, can be substituted with other tests. They include hydroxylamine, hydrazine, phenylhydrazine, and semicarbazide. Now, this semicarbazide, phenylhydrazine, hydrazine, and hydroxylamine can also be used to test for this. The reaction is also the same. What's actually going to happen is the removal of the oxygen from whatever compound this is, and hydrogen from the hydroxylamine, and the removal of, or hydrazine, the removal of water. Just know that whenever you're dealing with any of these reactions and they give you any of these 2 complex, observe something, remove your water. Let's use hydroxylamine for example. Hydroxylamine can be represented by this. This is, let me just start again. This is OH, if I may put, and this is N, and this is NH2, something like this. Now, like I told you earlier, what's actually just going to happen is the removal of this oxygen, and this is the carbonyl group, so this will just happen. And the precipitate to be formed. The precipitate formed in hydroxylamine is also yellow, Other ones can actually give different colors of precipitate, but let me not bore you with that. This just actually was going to happen, and then this ends up combining with this. I'm sorry, not that nitrogen. That's nitrogen. The other nitrogen here ends up combining with the carbonyl group, and that leads to the formation of the complex we're actually looking for. And that's just all the tests we need for like Brady's reagents and so on. Now the next test we're actually going to be talking about is the iodoform formation test. Now iodoform is triiodomethane, that is this CHI3. This is iodoform triiodomethane. Now iodoform is a characteristic reaction between carbonyl compound and alcohol. Now this test won't actually give you a final inference because there are two compounds which could actually do this test: carbonyl compounds and alcohol. Those are the two compounds that could actually undergo this test: a carbonyl compound and alcohol. So whenever you're doing this test, at the end of the day, in your inference, you end up writing carbonyl compound or alcohol suspected, but you can never conclude carbonyl compound. You end up mixing it because an alcohol could also do this reaction, and you might be dealing with an alcohol. So you have to actually go and do your Brady's test later on. But at first, let me just give the iodoform test. Iodoform, also known as triiodomethane, is a yellow crystal with a distinctive smell like that of a hospital. Now we all know that a hospital have all these distinct smell, mainly because of the iodine and whatever. The smell is always, I don't know how to put it, it always like irritates me in a way. And with this smell, we can actually identify if a carbonyl compound or an alcohol is present with the appropriate reagents. Now the reagents we could actually use sodium hypoiodide or sodium hydroxide in iodine. And this sodium hydroxide in iodine is just simple. It's actually still going to lead the function of sodium hypoiodide, and that's just something like this I2. That will just lead to the function of the sodium hypoiodide still. That's this plus HI. So this sodium hypoiodide, you can actually just prepare it by dissolving sodium hydroxide in sodium iodine. Sodium hydroxide in iodine, and that's what we're going to form sodium hypoiodide. So the major reagent is sodium hypoiodide. Now the conditions for the iodoform formation. Now in the alcohol or the carbonyl group, the major stuff that needs to be present there, it must be a methyl carbonyl, a methyl alcohol. If there's no methyl group present in that, iodoform will never be formed, and that won't end up giving us our results. So this test, now I'm trying to slim for it. Let me just try and like minimize it. Like I said, this test is actually going to be used to test for the presence of an alcohol and a carbonyl group. Now I'm actually trying to streamline it again because not all carbonyl groups undergo this test. Now the carbonyl group that will undergo this test or the alcohol must be a methyl carbonyl or alcohol. So we can actually see in our inference, we don't just write carbonyl, we end up writing a methyl carbonyl present or confirmed or suspected. It has to be a methyl carbonyl. No other carbonyl will undergo this test, and in my mechanism I'll actually show you why no other carbonyl will undergo this test. Now this is the mechanism of the iodoform reaction. Now let's use, like I said, let's use a ketone. So we have something like this. Now this is our methyl carbonyl. The R group can represent any long carbon chain. Now, like I said, reacting with sodium hypoiodide, NaOI. If we don't want to actually use this NaOI, we can just let me just put it in brackets at the top, iodine, ion. Now, what's actually going to happen? This is a three-step mechanism. The first thing that's actually going to happen is that this iodine ion will come, displace a hydrogen, and form this. That is, let me just say, a substituted methyl group, an iodine substituted methyl group, and that's actually what's going to be formed at first. Then this iodine, because we're actually, let me just include this 3 moles of this, so there'll be like other iodine molecules there, and they can actually displace hydrogen. Why will they displace hydrogen? Easy. If you can look easy like that, let me just keep going. So another iodine will come again, displace the second hydrogen. Please don't get confused. Another will come again, displace the third hydrogen, and that's why it's a three-step mechanism, because it occurs, the first hydrogen is displaced, then another hydrogen is displaced, and then the third hydrogen is displaced. So at the end of the day, instead of us having this, we end up having something like this. We end up having something like this with the I here and the I. Now actually what's going to happen again, let me just, now we've concluded that we've had this. Now let me just keep going with the mechanism. So let me erase all of this. Now we have this, a tri-substituted methyl group, double bond with O and single bond with R. Now actually what's going to happen, this occurs in the presence of water, if I may say. This occurs in the presence of water. So what's actually going to happen is that water splits into hydrogen, this H2O, splits into hydrogen ion and hydroxide ion. Now this hydrogen ion will come and attack this oxygen, and to lead to the formation of this. This is actually what's going to be formed. And now, for this to be formed, we end up having a positive charge here, because electron deficient. The carbocation will be formed because this carbocation is electron deficient, and now the bond that he was sharing with the oxygen ended up sharing, like the oxygen ended up sharing with the hydrogen. Now, due to this structure, these are unstable intermediates, and actually what's going to be happening is that this will actually like trying to undergo resonance to actually balance this. So actually what's going to happen is this bond here comes back here, and that relates. Let me just draw the two resonance structure. Let's erase this because I feel we're done with this. So let's just take this off and let's give our two resonance structures. This is our first resonance structure. So like I said, that bond will actually come back. So this is our second resonance structure. This I with double bond C, single bond O, single bond H, positive charge, and single bond R. Let's take this up a little, it's too low. Now these are our two resonance structures. Now, as you can see from this, the carbon is actually balanced. So what's actually going to happen is that it's actually going to lose this positive charge in this second resonance structure. And what's actually going to happen is that due to the fact that oxygen will actually have this charge, something like this. Now that's actually our two resonance structure. Now this intermediate, like I said, is unstable. So this tri-substituted carbon group, let me represent it with a different color. It's actually going to be kicked out in order to balance itself and to lead to the formation of this. The CI3 minus plus the C, let's say now double bond O, let's say the H is still here, and then the R group. It's still not balanced as we can see from this. So what's actually going to happen is that this carbocation, this hydrogen carbocation, is actually going to be kicked out also, and then it will actually live as a hydrogen ion, and we are going to use that hydrogen ion later on. That's just all is going to happen. So let's remove this. Now we all know that the hydrogen has been kicked out, so we have two intermediates that are now formed. That's this tri-substituted methyl group and this intermediate, and then this hydrogen ion. Now this hydrogen ion will end up coming again to bond with this tri-substituted methyl group, and that will lead to the formation of our iodoform, and that's just all we are meant to just see. That will lead to the formation of our iodoform, that is Ci3-. You can see it's electron rich. You can see it's electron rich. Ci3- ion is electron rich. Then it will end up combining with this hydrogen, which is actually looking for an electron, and to lead to the formation of this iodoform. This is the iodoform that we're actually looking for. And the methyl group, like I said earlier, that was the RC dot bond O. Remember now earlier when I said that the water actually splits to hydrogen ion and hydroxide ion. The hydroxide ion will now take part in this reaction and end up combining with this ion that is actually formed. This has a positive charge, and then to lead to the formation of an alkanoic acid. And that's just all that is actually happening here in the iodoform test reaction. Like I said, the methyl group needs to be present. Now this iodoform that is formed, that's what we're actually observing. This is a yellow precipitate, and like I said, it smells like hospital or whatever, how hospital smells, because of the iodine present. So that's just actually what's going to be happening. And when we see this yellow precipitate, we can actually conclude that what we're dealing with is a methyl carbonyl group. We can also say it's a methyl alcohol group, because alcohol and carbonyl group undergoes this reaction. And that's just all for the test of carbonyl compounds. Later on in further videos, I'll actually show you how to differentiate between aldehyde and ketones, but for now this is just test for carbonyl compound. So that's all. Thank you for watching. Goodbye. See you later.